Right. All right. Hello, kind people. How are we doing today? Yeah. Oh my goodness. Come on, people. It's Friday. Let's play. Let's play. You guys barely hanging on by a fingernail, I think. All right. It's gonna be okay. It's gonna be okay. Like I said, this section that we're covering is not too bad, right? Not too bad, right? Not too bad. All right. So let's start by kind of just going back over where we stopped. Again, we did this example the last time. Again, we're not using tables and all the other stuff. Get ourselves to an answer. All right, so question. The length of a pregnancy from conception to birth is approximately normal or normally distributed with a mean of 272 days and a standard deviation of 9 days. A pregnancy is considered to be full term if it lasts between 252 days and 298 days. All right. So first things first, right? This right here is a normal distribution. This right here is a normal distribution. And then they give us the mean and the standard deviation. And so that means we're halfway home, yes? Right? To solve this using SALT, the key word right here is between, yes? And so with that in mind, we should be able to get the probability. It says what proportion, again, recall that proportion and probability are asking for the same thing, yes? And so anyone's going to remember all these numbers? They can put them in SALT? Oh, I won't, but we'll try. 272 in 9 days. So where is my good friend SALT? Oh, there he is, my good friend Salt. Again, let me kind of refresh the page. So it'll kind of reset everything for us. Normally when you enter this page, you want to go over to your distribution calculators. And then you want to select normal distribution from the drop-down list. It's the first one. And then you want to go over and you put in the mean. The number of days was 272. That was the average. And the standard deviation was 9. Yes. And then, importantly, it says between, right? And so we're shading in between two values right here. So we click on between on our salt page right here. Questions there? Now, was it 258 and I can't remember. Oh, let's go back and double check. 252, that was the other one. 252 and 298. And so this right here will be 252. And then this right here will be 298. Right here. And again, see, it shades the regions for us. And then you can see the answer right here, 98.493% of pregnancies fall within the normal window of full-term pregnancy. Questions there? Also note right here, it calculates the two z-scores for us if we needed them. And you can see the z-scores down here, it was negative 2.2. And then over here, negative 2.8. You can see these are your two z-scores right here. And has shaded the window for you. Questions there? Comments, queries, concerns? All right, cool. So we got our answer 98.5, I think. They take much longer to get the answer. I see right here they got the same answer as us, 98.5, 98.49. Questions there? All right, cool. What else they gotta show us? I'm glad you guys don't have to buy a graphing calculator. These graphing calculators these days are like, an arm and a leg. Hopefully we can get pay for those no more. All right. That's the same question? Yes, same question. We covered all of this already. All right. So let's move to the next slideshow. That takes us to the other half of 6.3. So we're continuing 6.3 right here, areas under the normal curve. We've done this already in between. All right. This is when shading to the left. We've done, I think they put the same slides, but you saw these slides already, right? We did this before right here. You can either be in between to the left or to the right on the tails, yes? Those are our four possibilities right here. All right, so this takes us right here to the inverse normal distribution. The inverse normal distribution is us working the problem in reverse. The word inverse is a mathematical word for reverse. So in the inverse probability, what I will do is I will give you the probability, and then you have to find the score that gives you that probability. Does that make sense? So for example, I can say, how many days should a pregnancy last so that it'll be more than 80% of pregnancies, right? So I'm asking you how many days, I'm giving you the percentage. This is an inverse normal distribution. You're working these questions backwards. So we will give you the probability, and then you need to find the score. All right? Of course, SALT handles this easiest. Sometimes we need to find the X or the Z values corresponding to a given area. Okay? In those situations, what we are doing is we're finding the inverse of the normal probability distribution. Questions there? Okay. Example, researchers for quartz crystal watches have shown that the watches have an average life of 32 months before certain electronic components start to deteriorate, causing the watch to become unreliable. The standard deviation of watch lifetimes is 5 months, and the distribution of lifetimes is normal. So what's the mean? What's the standard deviation? Someone said 32 and 5 in their brain. That's why I didn't hear it. Yeah, this doesn't happen. All right, cool. All right. So now watch carefully. If the company does not want to make refunds on more than 6% of the watches it makes, how long should the guarantee period be to the nearest month? Right? So in other words, if they have a warranty program, if the watch becomes unreliable or unstable, they'll pay you for it. Yes? But they only want to pay 6% of people. That's their acceptable level for their business operations. How long should they make the warranty? Okay. Quite simply, the longer the warranty, the more people will be able to return things, right? Imagine that the average is 32 months. Imagine they put the warranty at 95 months. Basically, everyone will make a warranty claim, yes? And so they want to figure out, well, we can't set it for one day, right? So they want to figure out how many months they can set it for. And so that's what they're going to do right here. So the key thing right here is that because they want to make no more than 6%, in other words, they want 6% or less of the watches to need to be fixed. Does that make sense? Why it's a left tail test? Right? They won't set that time period, but 6% or less. And so this is what we will do in SALT. So I go to my good friend SALT. Let me reset. What was the mean again? What was the standard deviation again? 5. And then I select a left-tailed test. Have I lost anybody so far? I've just put in the basic information right here. Okay. Now here's the key. In the previous section, we would put a number inside this box, yes? 42 months, 22 months, whatever. In this scenario, because we're doing the inverse probability, we put the probability we want instead. So we put in 0.06, which represents 6%. Yes? Yes? And the number up here will be the answer to your problem. It needs to be less than 24 months, 24.2 months. Questions there? And so this company will give you a 2-year warranty on this watch, right? A 2-year lifetime warranty, like they like to say, right? Right. And that's why whenever you buy anything and the warranty is 1 year, exactly like a day after the warranty, it starts to break. No, you guys haven't experienced that yet? Oh, it's coming. It's coming, right? You know, you buy a phone 2 years after the 2 years after the date you bought the phone, it starts acting weird. Yeah. No? Okay, fine. You start looking at it for now. But this is why they did the math. They had a probability. Most companies like 5%, 4%. And then once they go past that mark, that's when the warranty ends. And so, questions there? And so the number we're looking for is 24 months. So they put the information in onto SALT, 32 months, sigma is 5, and you put in a probability or proportion of 0.06, and then you read the value off. So we're not going to be looking stuff up on Z tables. Oh, we're not going to be doing all of this. Oh, we're not going to be doing all of this. Because literally you had to find the Z-score, estimate the Z-score, and then unwind it to get the score. But look, there you go. Got the same answer as us 5 hours later, 24. Questions there? Questions there? All right then. Inverse normal in between. Now these are a little bit tricky. So, but let me see if we can get an example. I don't know why they have all these again. Did I make a copy of this thing? Oh, they just did it again on the calculator. All right. A relay microchip in telecommunications satellite has a life expectancy that follows a normal distribution with a mean of 92 months and a standard deviation of 3.3 months. When this computer relay microchip malfunctions, the entire satellite becomes useless. A London insurance company is going to insure the satellite for $50 million. Assume that the only part for the satellite in question is the microchip. All other components will work indefinitely. For how many months should the satellite be insured to be 98% confident that it will last beyond the insurance date? I'm going to let you try this one in salt. Let me underline the key numbers for you to give you a fighting chance. Let me see what answers you get in our good friend salt. This insurance company clearly doesn't want to pay out, right? I mean, 2% chance that they actually make the payout. Again, the hard part about these questions are the word problems. Because you kind of have to script what they're trying to say. One of those key ways of is underlining key information or rewriting the key information, or at least restating the key information in your own words. Those things kind of help you figure out. Also, some common sense makes sense right here, right? They want to be 98% sure it goes beyond the insurance rate, right? The average is going to be 92 months, yeah? The average is 92 months, right? So if the insurance company says 92 months, then only half, there's only a 50% chance that it will be on that month, right? Yeah. So the answer has to be greater than or less than 92 months. That's bigger than enough. The answer should be more than 92 months or less than 92 months. It has to be less than 92 months, bro. Because think about it. If I said, yo, I'm going to allow you to use this satellite for 500 months. There's no probability that they could really have a small 10% chance. The shorter the number of days, the higher the probability is going to be, yes? That they don't have to pay. Yeah? All right. All right. Let's go ahead and, so again, so you have your picture right here. So the key thing right here is we're looking for a number down here because we want them to go beyond this date. Okay, so what's the mean? Mean is 92 months. What's the standard deviation? 3.3 months right here. Is it left tail, right tail, both tails, or between? It is a right tail. Yes. And what comes down here in the box? 98% or 0.98, like so. And so the answer is they should insure it for 85. Question there. Yeah. Say again? Oh, because they said more than or beyond or larger than or greater than or above. All those things means we want them out to the right. Right tilted. Anybody else? Anybody else? All right. So let me work this thing out for us. 98%. Find that value. All right. So again, so this is kind of harder to do, but they get the same answer as us, 85 months. Question done. All right, so that's the end of 6.3. Inverse norm. 6.4, 6.5. That I have one slideshow for the two of them together. What time is it? Is it 9:41 already? It says it's 9:40. We got here early, 9:40. All right, so we'll do just a little bit of sampling distributions. I always have this problem. I can't get too far ahead, but I know I have a in-class homework that's coming. In class, yeah, it's coming. I gotta think about this. All right, sampling distributions and the CLT, the Central Limit Theorem. Do you guys remember our very, very, very early discussions about populations and samples, parameters and statistics? Yes, when a number comes from a population, it is called a parameter. And we use these Greek letters or capital letters to represent numbers that come from populations. Yes? This mean right here means not only is this an average, this is an average of everybody. Yes? So if the people I'm talking about, the students in this class, if I wanted to find, for example, your average grade, I will need to take the grade from everybody in the class. All right? So I'm going around, hey, what's your current average? What's your current average? What's your current average? Yeah. On the other hand, a sample is when we take a value from a statistic is a number that comes from a sample. Yes. Right now, the entire class is not here. Yes. So if I just asked you guys what was your average on your test, then that would be a sample for the class. All right. Again, because of that, the letters they use are different. They use X bar, S squared, and P hat for proportions. We'll get the proportions in a little bit. But they just want to remind you of this right now because we're about to use them again. Let me ask you a question. If I take an average grade for the students in this class today, and then I wait until Monday and I take an average for all the students who are in my class on Monday, will I get the same answer? Assuming no one did any work on the weekend, will I get the same answer? I will not get the same answer, right? Because what happened is the population will have changed. Well, the sample will have changed. Some of you guys may be sick on Monday. Some people who were sick today come in on Monday, and so I will get a different answer. Yes? If I was to wait until next week Friday and then take a third sample, I would get a different answer. Yes? Right? And so we can ask the question, what is the average of the averages? We can ask the question, what is the standard deviation of the standard deviation? Yes. When we're doing this thing right here, we're doing what's called a sampling distribution. A sampling distribution is the idea that if I take the same group of people and I go take a sample, I go back, I take another sample, I go back, I take another sample, right here, those numbers themselves will create their own averages and their own standard deviation. Yes. A common example is that every student who leaves this university has to take an exam before they leave, right? It's supposed to help them figure out if you guys are learning anything or not. But you guys, every student before they leave has to take an exam. So every single year they're taking that exam, right? Let's say the first year the average was 95. The next year the average was 94. The next year the average was 96, right? That's going to set a group of numbers, yes? I can take the average of those numbers. Yes? I can take the standard deviation of those numbers. Yes? Whenever I am doing that right here, I am doing what's called a sampling distribution. I am breaking down a distribution of a distribution. Questions there? So in other words, this sample might be the class of 97. This class might be in the class of 97. The average for that class on that test was a 92. This right here might be the class of 98. This might be the class of 99. This might be the class of 2000. This might be the class, last name. This might be the class of 2001. This might be the class of 2002 and so forth and so on. So right now, I might have 50 numbers. Yes? Oh, maybe not. Well, if I do it 3 times a year, I might have 50 numbers. 50 numbers. But the point is, I can take an average of all those numbers. Yeah? That's going to be an average of averages. Yeah? I can take a standard deviation of these numbers. I can find the mean of these numbers. I can take a standard deviation of these numbers. Right? This average of all the average is called a sample mean. Questions there? Questions there? It turns out that when you do a sampling distribution, certain things fall out to be true. The first thing that falls out to be true is that the averages of the average itself will be a random variable. Does that make sense? The averages of the averages will be a random variable because it's going to be a number and it's going to be random, yes? Because I cannot predict what the next class score is going to be, I cannot predict what the average is going to be. Okay? Yes? But it turns out that the mean for the sampling distribution is going to be the same as the mean for the regular test. Let me write that down. So let's say for the last 5 years, the average score on the test was say 92. Right? For that same score test I'm talking about is leaving right here. The average for that test right here is 92. Yes? If I use a sampling distribution, so in other words, if I randomly picked 5 for the last, 50 years, if I randomly picked 5 of those right here, and I took an average of those 5 random classes, that will also be 92. And so what this is basically saying is that the average of the average is going to be the same as the average. The key thing you need to remember is that the two things are the same. All right, let me put it to you this way. Let's say test 3 coming up is the easiest test in the class. And so the average for this test is going to be 80. Okay, that's what, if you about to take this class, your average, your expected score is going to be 80%. That's your expected score, right? If I took the whole class together, I want to find what's the average for the entire class, that average will still be 80. That average will still be 80. Does that make sense? If your average is 80 and your average is 80 and your average is 80, then the average for everybody in the class, if I take the whole class as a group, the average will still be 80. Yes? And so this is what they're trying to say right here, is that the average for the sampling distribution is going to be the same as the average for an individual in that group. Questions there? On the other hand, however, the standard deviation is not going to be the same. If you think about it for a second, in this class right here, the average might be 80, right? But somebody in the class is going to get 100 and somebody is going to get 60, yes? Right? And so for this class, the average score, if you are taking this test by yourself, your average score is still going to be 80, but the standard deviation is going to be huge. It might be like 20 points. Well, make 10. The average is going to be 10. So you either on average score about 10 points above or 10 points below 80. Yes? Yes? But the sampling distribution, on the other hand, the standard deviation is going to be much smaller because the average for this entire class is going to be 80, yes? If I go to another class, the average will be 81. If I go to another class, the average will be 79. And so if I take the standard deviations of those scores, the answer, the standard deviation I'm going to get is going to be much smaller. Okay? And so because of this, we have this right here. The standard deviation for your sampling means is going to be the original standard deviation divided by the square root of n. If I'm dividing something, will it get bigger or will it get smaller? It will get smaller. And so because of that, the standard deviation for the population is going to be smaller. It's going to be this divided by a radical n. Questions there? Let me see if I can show you to you this in a different way. Let me show it to you in a different way. Before we get to CLT, what am I looking for? Where is it? Let me just do it this way, faster. Hey, where is mine? I'm missing a slide. Is my last slide? I'm missing a slide. I'll have to go look for it. Anyways, I digress. All right, so the moral of the story is before I go back all of this, because I'm going to stop right now. The moral of the story right here is when you're looking at a word problem right here, what you need to see is whether or not they take a sample or not. So you see right here, based on data from the US census, the mean age for college students in 2011 is 25, with a standard deviation of 9.5 years. So if I was to pick a random student, the average age would be 25, and the standard deviation in that age would be 9.5, right? If you, on the other hand, instead of picking one student, I pick 125 students, right? And then what's going to happen is that what's going to happen right here is that the mean for the group of 125 students, the mean for the sample for the 125 students is still going to be 25 years old. But the standard deviation for the group of 125 students is going to be 9.5 divided by the square root of 125. Because I am sampling 125 students in one go, the standard deviation between groups of 125 students will be smaller. And so because of that right here, we use this number instead. And because of this, this number goes by a name. This number is called the standard error. You need a calculator to get that answer, most likely. 9.5 divided by radical 125. This number right here is called the standard error. Questions there? All right, so clearly I need to say all of this again on Monday. All right, we'll try again on Monday. Let me send you guys on.